Yeah, I have to. The colors are not getting through on the screen, so I will explain a bit. Like you will see a rectangle, a circle, or something. We'll manage anyway. So here we go. The first question is: who does not know soil, or what soil is? Wow, that's really cool. But yeah, there was hands. So soil is an object-oriented database only made in Pharo. So there is no special library support something. It's all Smalltalk. And the duty of the object-oriented database is to make persistency as frictionless as possible, which is usually not the case. Yeah, the last years, I think soil is already 4 years now, and in the last years, we talked about what it can do for you, but also there is a bit always these like it's a toy or it's not a real database stuff. So and I ask around, and so this year is like how it works, how it does the stuff. So I was expecting a 45 minutes talk, so to have a Q&A at the end, but. We'll see. I'm not sure how far it goes, but I will start, and then maybe there's a point where the questions are imminent or not, and then I will stop and we will do the questions and answers. So lazy me, I wanted to do this this morning. I didn't do it. I will do tomorrow or the day after. So there was a new release, as is usual in ESUG. So for all they know is that the good thing about soil is that it's small, it's a database. The bad thing is that you have still to use a bit of low-level API. So, and one of these calls was markDirty. This is when you change an object, you had to tell the database that now that the object is changed and should be saved when you commit a transaction. So, and this is gone. So now we have automatic object tracking, and now you don't have to use this call ever. So, which is a great thing, by the way. Okay, but let's start at the beginning to get everyone at the same plate. So what's the problem soil tries to solve? Is persistency. So usually, so my personal view is that persistency is also always a drag. So no matter what database you use, whether it's always difficult and it always gets back onto you without. Either you have in an SQL where you have to restrict the models you save or anything. It's not something which I would call fun. So let's start. But the good thing, and here there's a blue big circle that's blue. On the model there's a smaller which is green, and then there's a really white one which is for the object. So when it's about, I mean, we have a database which is the image. So that's why I wanted to start from there, because usually we can just save the image, which is the perfect store for objects, because you read it back and you get everything exactly how you stored it. So there is no better way storing objects. So from this, image persistency is really good. But there are reasons why it's not so good. So now you see at least the circle is, if we only save the image, we write all objects. All of the UI, Morphic, your model, everything else, yeah? And then you see maybe that's not. So it's a huge, well, in the best case it's about 20, 30 megabytes, but it's easily 100 megabytes when we load our product. So we can say that storing 100 megabytes multiple times per second is probably not the way to go. The second problem is, in order to store a sane graph, it has to stop the world. So the VM just stops every processing, which means everything that could change an object while it's saving the thing to disk. So I did soil for ActiveGrid, which is a SaaS product, so internet product which gets HTTP requests. That would be not so good to stop the world every time you want to save. So when it contradicts, you store it less often or more often, it doesn't work pretty well. And one good thing about databases is that usually you're freed from the limitation of main memory. For the image, this is not the case. The image fits in memory or it doesn't, so there is no way around it. So the next thing is we have already a serializer. So there's already the circles, and here now we're concentrating on the model. So there's another way. We have fuel, which is the yeah. Oh, here. So I made a point for that. So you can go say, if UI storing, everything storing is too big, so just let's make it smaller. And we have fuel, which is a nice serializer. You can just my domain model, and it just store my domain model, which should solve a bit of a problem. It writes only the model, which is usually still big, which is still making the problem a bit smaller, but not making the problem go away. Then there's a problem because it does not stop the world. So because in an object graph like the image, if you have a service, usually these objects would be shared between different requests, processes. So, and that means if you would store the data, every modification in between while it's being written would be altering the stuff, maybe leaving a corrupt database or a corrupt data on the disk. So this is also not pretty good. And also it's limited to main memory because it's always acting from the image, and I can only store what I have in main memory. So yeah, so and to be complete is the object level we didn't consider right now to make every object storage on its own. So, and while doing soil, it was always like the definition of database. My last talks, if you saw those were about the magic when talking about databases, because everyone thinks there's some magic. But a database you can define probably, if you can write, read, and query. Query means a subset, so you can have more memory on disk than in main memory. And the object graphs in an efficient and concurrent safe way. That would be a definition of the database I use for my service. Okay, so you might see that I left a little bit of gap. So if the object is not the grayness level, and the image isn't, and my model isn't, maybe there's something in between, which we could call a partial graph. So if I don't want to store the whole model, I can just make a little bit of it. So how do we do this? So a partial graph means, that's a bit shitty. There's pointing to other objects. So a partial graph is just like you can isolate some objects in between your big model that you define as a partial graph. What's the hope? What brings it to is because a partial graph we can make really small. We could even make it one object. So and then it gets really small. So that means reads and writes should be really fast compared to storing all the model, all the image. Soil does it in a way, it uses transactions for that. So it's not the image session level, but it uses a transaction, which is another scoping mechanism for my thing, which is, so for a service like the HTTP service, if you have a sync server, for each request there is a process spawned. So, and then you attach the transaction to a process, and then you have already a setup saying multiple processes do different data. And every partial graph is written by each transaction and materialized by each transaction. So that's how we can enable concurrency, because no matter how many processes you have, each process has its own copy of the object, so there's nothing shared, so no problem. And as we have the query, we have partial graphs. It also obviously brings that we can have on disk a much bigger model, because we only load partial things. And so there could be petabytes on disk, and we just pick the ones we really need. All right. So the way how we do partial graphs in soil is a call which is make root. Well, we call it now, it's not the best name, but it's now called a root object. The root of that partial graph that you're trying to manage. And it's up to you. So that means the scope or the size of the partial graph is defined where you call make root. So you can make it really small, you can make it rather big, which is totally application specific, which is the best way to put it. But you have to put it. This is the leftover low-level API that you have to use if you use soil. When you make an object a root object, it means it gets an address from the database, which makes it resolvable. So I can just go to the database saying, I want to have this one, which is usually not the case if you store all the object clusters. And the root objects also help defining the traversal boundary. And this is like, you see here, there's pointing. Here's the 1.3. Some other object is pointing to my partial graph. And here I end up, so here's leaf nodes. And here's other addresses pointing to other partial graphs. But here we define the boundary because we stop traversing there. Yeah, so here you have leaf nodes, which is the usual. So if you traverse something, if you have a leaf, you start returning, no problem, no endless loop. And for the reference as well. So because a reference is then reified, we don't go to the referenced object. We're just saying this is a reference, and a reference is also a leaf. So we stop here, and that defines the boundary of the partial graph. The next thing we need to do, if we have that partial graph, is it's all bytes, yeah. But this is how it looks in memory, and this is how it needs to look like on disk. So we need to have a way to get that partial graph onto disk. And there's one thing which is really helpful because Pharo has not only classes, but every class has a class layout. So the typical things are normal objects. These are the usual type. They have instance variables. So we have 4 instance variables. So it's a fixed size object. And there's collections, which are variable length objects. And it's obvious both of them need to be written in a different way. So as we are delegating the serialization to the class layout, it's already solved in a polymorphic way. So in each layout, we just implement a way how we store that memory thing onto disk, and we're done. So and this is a general case because that we can do for all objects. So, but there's special objects, and one of the objects are immediate objects. So here it might be a bit complicated to go over the class layout just to figure out that you need to write the content directly to disk. So you can just overwrite the method, and then we make this for immediate objects, and this case is solved. And there's other custom needs. So string is something which we just want to optimize, because if we Soil happily stores a string, but then it goes, oh, you're a collection. Ah, I'm writing the collection, then, you're a character. And then it starts to write a structure for collection, and then for each character, which might be even 4 bytes long. And then we don't, as with that, don't want, we just overwrite it here and put a custom implementation, something like just write the whole thing as UTF-8 string on disk. We can just shortcut this and optimize the way how we put things on disk. The second good thing about class layout is that for serialization, materialization, and the automatic object tracking, we need a deterministic way of traversing the whole graph. But with the layout, we can see that there is only the layout defines for index, and for variable length, it always defines the order. So you end up having objects that have a defined order that you can use for traversing, or things like hashed collections that do not depend on order. Yeah, so the maximum you can have is in a special condition for a set. When you load it back, you have to rehash. So that's something like it would put the things back, but at the wrong position, which collides with the hash collection. But then you would rehash. So in the end, we could say every kind of object we can traverse in a deterministic way. And that's how the automatic object tracking works, because we have a recursive hash. So it goes recursively through the partial graph, and makes operation on the basic identity hash to make a hash for the graph. So in this way, we know when the transaction is committed, we do this again, and we know exactly which of the partial graphs have changed. If it goes too fast, or if something is really not comprehensible, just stop. Yeah. So the storage format in Soil is that. What? That's a question. A question. Yeah.
What is a class layout?
A class layout it defines the memory structure in memory. So if you have an indexed, so every object that well, every object has a class, so there's basically two types. So every object has a hidden instance variable, you call it, which is the first, and that's the pointer to the class it belongs to. So that's every object knows its class. It's the first instance variable, which we don't see. And then you have, for instance, if you define 4 instance variables, the fixed layout will say, right, there's 4 of it, and you could just go from 1 to 4, and then go through. For variable lengths, it's just like that the size is known internally, and then it knows that there's an array. There's for immediate is also a layout. So it's just the structure that you need in a reification of the structure in memory. Okay? Good. Yeah. In order to make so I'm just saying the two main objects are objects with a class, yeah, and immediate objects. So, but immediate objects have in the object header, there's a few bits which define which class it has. So, and this is a really nice trick that every object in Smalltalk can have a class. And for optimization reason, we reify that when writing it as bytes to the disk. So the first one is always a type code. It's a single byte, which is defined here. So if there's no special custom implementation, it's just 1. And then it goes over the class layout and blah, blah, blah. And if you want to go optimized, especially something like positive and negative integer, so this is usually stuff that you either reserve a bit for the sign or do something wild. We can just make it in a type code. And then we always read a positive integer. And if it's a negative, we just negate it afterwards and we're done. So this is it's a longer list. And there's another dictionary that just resolves that type code to the factory, which can read back the stuff. And here it's a block which uses the materializer. And here, for the most cases here, the class, it's just a class side method that's used then. Okay. Okay. But there's a speciality which which Pharo does not have, but Gemstone has, is that if we store objects, it can live there for a long time on disk. And if we read back, there's no guarantee the class is still the same. So we know not only the class layout, but what were your instance variables you define, and the order. So, because even if you flip 2 instance variables, you don't want to have the contents flipped in the object. So what we do is, if we take a class, we call it behavior description, because I'm not the biggest fan of classes. That's the reason. But then we just make it that this is the class number, there's the instance variables, foo, bar, blah, 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 in that order. So, and then we write it to disk to be assured if you change the class or something and read that object back, you still know what it was then. Next thing is that behavior descriptions have versions. So they're all stacked. So you store one object with an old version, then you change the class and you change the next object, and then it makes another behavior description with a new version and stores that at disk. When you read back the old one, it just sees, I'm not a current class. And then it takes all available class versions, and then it migrates the object to the class which is in the image. So because Gemstone does not do this, because it doesn't have to, because it has class versions, so there is an array of older versions attached, and so they can just leave the object with the old classes. If it's okay, they use the old compiled methods. So, but we in Pharo, we don't have that, sadly. Would be a nice addition. So, but Soil does it, because we have no other way of dealing with objects which are pretty old. Yeah. So every object needs to be converted on read, because we have only a single class, a global one, and so there's no other way. But it's not a big problem.
For now.
For now. I wanted to point to you. So the next thing is, how do we store that on disk? So we have now find a way to have the partial graph going into a byte array. But it's always good to have a bit of metadata stored along with the bytes to know what you read back. So everything, the bytes, that's what we just serialized. And then Soil takes a cluster record, which is a list of versioned object IDs, which reflects exactly what I told about the behavior descriptions, because it not only has the address, but it has also the version. So now I'm saying, I'm class foo at version 2. And so I take the old version, and what I read from disk, I use that in order to read it and then to migrate. It also is a list of object IDs is the addresses. Yeah, it's also the references it points to. So I have a partial graph, and it points out to other objects. We have that in the cluster as well. I will tell immediately why. And there is 2 versions included because we want to have MVCC, which is an acronym for multi-version concurrency control. Because a lot of databases do this, is that if you have, just imagine you open 2 transactions, I open one, another one opens one, changes my object and commits. What happens? Do I get the new object or the old one? So now Soil makes sure that whenever you held a transaction, you read the objects when I created the transaction. Every transaction in between does not change the data. You get a sane state of that. And this is because if the, for instance, I think there's a slide which I can explain it better. Yeah. So the reference and all the things in a cluster record we do because we want to treat a database as a database and not make it too dependent on the application model. So here you could make analysis like who is using old classes, yeah, who is using an object. So you can there's a visitor-based thing in Soil where you can process everything in a database without having even your code loaded. So that's the boundary we always wanted to have. On that level, or the low level, you can make the database level. It will tell you which names the class have and everything, but you can use all of that stuff. Even if the GC, a basic GC, would work without having the classes of your application model in the image. That's the reason why. Yeah, and that would be an explanation of the MVCC. So we have here, that's the structure, how you write on the disk. So you have one file which is couples of 8 bytes. That means 1.3 we had. 3 is the index, so it's a 3 times 8. I just jump to the file at 24 bytes, and then I can read what's in there. So this is like a stack. This is also the same 8-byte aligned, so I always know if I have the one index like 1 million something, I just multiply and then I jump into the file. And here you will find the address where in the heap file, I mean it's similar to how everything works, it points to the position in the heap file where this record is. So what I explained with the MVCC is that I open my transaction, and I'm on V1, yeah, and someone else opens a transaction, commits, and puts the database in V2. And then I get to read that object. What happens? Because that address is overwritten with the new one. So you read scoped on your read version, it's called. My read version is version 1. So I have 1:2. I read what is there. I go here saying, what's your version? V2. I'm saying, well, mine it's V1. I cannot see this object. But there's a previous version pointer. So I just go back as far as it needs until there's a number I can see, which is equal or lower than my own number. And that's how you get it, that you can support a sane state while leaving everyone commit. You just make the detour of jumping down the pointers to get that object how it was when I commit, or when the one before me committed it. That's the thing I can see. I don't know. The slide could go forever. Soil tries to be a nice database citizen, and most database citizens try not to lose data. And one of the ways not to lose data is that every write to a disk is twofold. There's a so-called transaction log, which is a binary file, which is only appended only, where you write low-level things like there's a new object with something, there's a new version of an object, there's a new key in the index stuff. And that you write to that file, and then you call fsync, which is in in Windows I think it's called different. Fsync means, because every operating system, or the image is like, I want to be fast. So usually, if you write something, it's not put on disk immediately. So for Linux or something, you let the kernel do the stuff. But if you want to assure it's on disk, you make an fsync call. And then it flushes all cached pages for that file, flushes to disk, and returns when it's ready. So when this call returns, you know the data is on disk. And then you could start and write to the heap file. Yeah? So, and then you have a situation that you're saying, okay, there's one thing. There's another file pointing to the last. No, forget it. No. Yeah, then you write to the heap file, and then you can say just, okay, before I commit and the image dies, no problem, the transaction is just gone. If you started to commit and it crashes while you're writing this transaction file, on next start you will see, I'm not at the newest state, there is one, but this is super broken, so I consider this also not aborting. Yeah, I just ignore that stuff. Then you crash while writing to the heap file, but then on the next start you say, oh, there's a new commit records. It's committed, so just replay that stuff. And then you just do everything you did to the heap as well. And the way the index files and everything is structured, you will have a bit of garbage, but the state will be the same because you reapply all the commands. And even if you have them partially before, they will be redone. You will have some bytes left over, but it does not affect the reading or writing of the database. It will be the same state. And then there's checkpoint that if you succeed to write the transaction log and write to the heap file, then there's a so-called checkpoint record that you write in another file that points to the last successful turnaround. And from then, it looks always in the transaction log saying, oh, the last successful over here. Is there something after in the file? And that's the whole process. So, yeah. Okay, this is the last. Yeah, so this is a bit of the general structure of the database, but this is not super important. Maybe if there's questions, this might be.
Thank you, Norbert.